Hi there, welcome back. Today I'm going to talk about Hazard, which is not a former Chelsea player who joined Real Madrid, but something that happened in the circuit. Namely, there are some problem when we're dealing with circuit because so far we'll be talking about circuit, but we kind of use them and so their behavior in a kind of idealized world. But we live in a real world, not in an ideal one. So it's worth seeing what how a circuit really behaves. And this has to do something with the cardinal maps. So this is basically the reason why I've been waiting so far to introduce hazards. So let's just make an example, right? Let's draw a circuit. In particular, let's draw something like, I don't know, an AND gate that takes an input, this one, which is our P. We're going to call this P. And another one, which we're going to call R. And we're going to invert this, okay, like so. So this is a simple NOT gate that goes into an AND gate. And the output from this AND gate goes to an OR gate. So this is an OR gate. And we have something else here. We have this other AND gate, which goes into the OR gate as well. But here, I'm going to have one of the input as Q, and the other one is going to be from R. Okay, this is a perfectly valid circuit. It's fine, right? So what do we get? Well, if we draw this circuit, right, we will get PR. So this is going to be the end between P and R naught. And over here, we're going to have Q and R. So this is going to be QR. And over here, the OR, the final output from this, is actually going to be P R naught plus, so OR with RQ, so QR. Okay, because this one will be actually P times R naught, because there is a naught here. And over here we would have R times Q. And if we put those together, we get PR naught plus or with QR, or RQ is the same. So this one here would actually be our function. So we can write this as our function, f of P Q R equal to QR plus P R naught. It is as simple as that. Now, if we are going to actually make the truth table out of this, and we can, what we're going to get is going to be this. So if I write the truth table from this, let me just do it real quick. So our input is P. Let me just put it as Q, R, and P. And our Y is going to be our output. Okay. So if I actually make the truth table out of this, let's start. I have 0, 0, 0, 0, 0, 1, 0, 1 0 0 1 1, and then we're going to have 1 0 0 1 0 1, and lastly 1 1 1. So those are gonna be our combination, right? And as y, we would have, well, in this case we'll have 0 times 0 plus 0 times 0 naught. So it will be 0 times 0 is 0 plus 0 times 0 naught is 1, but it's still 0 plus 0, so it's 0. So it stays at 0. Now, if I do this, what we are going to get is going to be 0 times r, which is 0, plus p, which is 1, times r naught, which is 0 naught. So 0 times 0 is 0, plus 1 times 0 naught is 1, so 0 plus 1, so it's 1, so we get 1. Here we're going to get, well, 0 times r is 1 plus p is 0 times r naught, so 0 naught. So 0 times 1 is 0, plus 0 times 0 naught is 1, so 0 plus 0, so it's 0. Then 0 1 1, we will get 0 1 1 is going to be 0 times r, which is 1, plus p, which is 1, times r naught, so 0, sorry, 1 naught. So 0 times 1 is 0, plus 1 times 1 naught is 0, so is 0 plus 0 equals 0 once again. So we get 0. And now with 1 0 0 we get 1 times 0 plus 0 times r naught, so 0 naught. So 1 times 0 is 0, plus 0 times 0 naught is 1, so 0 plus 0 is going to be 0 once again, so we get 0. Now with 101, what do we get? Well, 101, we get q, which is 1, times r, which is 0, plus p, which is 1, times r naught, so 0 naught. So we get 1 times 0 is 0, plus 1 times 0 naught is 1, so we get 0 plus 1, so it's 1. Then we get 1. And then with 1 1 1 we get 1 times 1 plus 1 times 1 naught, so you get 1 plus 1 times 1 naught is 0, therefore we get 1 plus 0, which is 1. There's something I'm missing. I might have made a boo-boo here. I don't know whether it should be another one, I think. Maybe not. So 0 0 0 0 0 0 0 naught, so this is definitely 0. 0 times 0 plus 1 times 0 naught, so yeah, this is 1. 0 times 1, which is 0, plus p, which is 0, times, yeah, this is 0. 0 here, times r, which is 1, is 0, plus p, which is 1, times r naught, which is 0, so yeah, now 0. And then here we have 1 times 0, which is 0, and then we have p, which is 0, times 0 naught, which is 1, so it's 0. No, it's fine. So we got these truth table, and we can draw our basically our kernel map out of this. And the reason why I'm going to do this is going to be you're going to understand this right now. So let's just draw this, okay? If you remember how to make a kernel map, you have 0, 0, the gray code, so 0, 0, 0, 1, 1, 1, 1, 0. And here you have 0, 0, 0, 1, 1, 1. Oh, well, shoot. No, just with P, so you only have 0, 1. Yeah, I got used to draw way larger kernel maps. Let me just... yeah. It's gonna be like this, and like this. Okay. Therefore, we are going to have QR over here and just P here. So if we follow the map, we're going to have when QR are 0 and P is 0, the output is 0. When QR are 0 and P is 1, the output is 1. When QR are 1 and P is 0, the output is 0. When QR are 0, 1, and P is 1, the output is 0. Now when QR are 1, 1, oh, there is something missing. Yeah, there is something, oh, I was sure I made a boo-boo here. Well, this one should actually be 1, 1, 0, and this one should be 1, 1, 1. Yeah, so with 1, 1, 0, we have P here, so this one should be a 0. 0 times 1 naught, so nothing changes. It's still 1 plus 0, which is 1. And over here, we did it before, and it's definitely going to be a 1. So yeah, so when QR are 1, 1, and P 0 is a 1, and when Q and R are 1, 1, and P is 1, the output is 1 as well. Here, when Q and R are 1, 0, and P 0, the output is 0. But when Q and R are 0, 1, 0, and P is 1, the output is 1. So this is a normal kernel map. So I know what you're thinking. You're actually thinking like, well, I know I'm gonna make, a group which includes prime implicants. So if I'm gonna make using min terms, then I'm gonna say, okay, fair enough. I'm gonna say where those are when Q is asserted. So when Q is 1 and is asserted here, when R is asserted, so when R is 1 and is 1 here, and when P is 1 and is 1 here. So now I can say, okay, I'm gonna make the groups, and those groups have to be with the maximum order with a power of 2, just like we did before. So I'm gonna say 1, 1, and 1, 1. So this will give me a perfectly valid solution. But there is a problem. Now, you see, if we go back to this circuit here, right, there's actually a problem here. Because, this is an AND gate, this is an AND gate, and this is an OR gate. But what does this AND gate takes? Well, it takes P as an input and R not as an input. This is a problem because you expect this not to be, yeah, just take the value of R, invert it, and put it to AND. But this is not something that happens instantaneously. This is, in real life, when you draw an AND circuit, a circuit with an AND gate, this is, something physical, like a real chip. And this one is a real chip as well because it's a NOT gate. So whenever the input goes into here and gets inverted, it creates a little bit of delay. But notice that this delay is not present here when there is the other AND gate, because it basically gets the R input straight into this and the Q input straight into this. So there is a problem. Let's suppose that we take our input as what do we get? Well, let's suppose that we get, I don't know, like 1 1. Well, no, 1 1 is not going to pass, so 1 0. Okay, 1 0 is going to be our input. So 1 goes here, 0 goes here, it becomes a 1, and it goes here, so it's a 1, 1 and 1, and the output is 1. This one goes to here, and here we have a 0, okay, so 0 is here. Q, let's suppose that Q is 1, so 0 and 1, this is not going to pass, so it's going to be 0, and then here we're going to have 1 and 0, so 1 or 0, at least one of them has to be 1, so the output is going to be 1. So far, so good. But notice what happens, right? Notice what happens. Let's suppose that now I'm going to turn this one to 1. So I'm going to have 1 here. If I get 1 here, then I'm going to get 0 here, we are not. So I'm going to get a 0 here, we are not. So 1 and 0 is going to give me a 0, okay. And over here, I'm going to have 0. What happens here? Well, I have a 1 now, so it gives me a 1. 1 and 1, then this one is 1. So 0 and 1, the output is still going to be 1. There is a problem though. When I switch this one from 0 to 1, before it got to 0 here, okay, there was a teeny tiny moment in which this one was still 1, because the NOT didn't actually happen, but over here, this one was already 1. So let's suppose that we had this one, which was still 1 here, was not 0 yet. 1 and 1, the output was going to be 1. And over here, okay, we had 1 and 1. So the output was going to be 1. So 1 and 1 was going to be what this OR gate was going to see, and the output would still have been a 1. But what if we had something like this? Well, in that case, the output for a teeny tiny moment would have been 0, because both the inputs were going to be 1. But this was not actually expected. We expected it to immediately change from 0 to 1 and 1 to 0. But that didn't happen. when you write circuits, okay, and you have P, R, and Q, you will have something like this. You will have P, which goes to 1, okay, and it's 1 all the time, like 1, and P is 1, okay, or something like this. For R, you would actually have, if you were going to get from 0 and then a not going to 1, then you will have something like this. So this is when the not gate actually, does what it has to do and invert it to 1. So there is a teeny tiny delay. And for the Q, instead when it's set to 1, it's just gonna be 1 all the time, right? So it's not gonna change. But it is Q and it's 1. Now this is a problem because, as you can see, there's gonna be a point in time in which, this one has the right value, this one has the right value, this one has the right value in input, but this one does not have the right value in input. And it's going to be a problem, especially when it comes to here. So what do we do? Well, do we have to, try with our circuit all the time and think about this and so on and so forth? No, there is a better way. If you are already in the Cardinal map form, you can say, okay, if you have, it's fine if you do a group of, like this. This is basically a, a group which has those elements. So group of 2 and a group of 2. It's the minimum cost of components is covered, but there is a risk for an hazard. And this is a static hazard which can happen because of this reason, because of this not here. So what you want to do is look at the map basically and say, okay, if there are, if there are two ones, one close to the other, of two different groups, then there is a chance for an hazard. And what you want to do is add an additional group, which is going to add an additional circuitry, but at least it makes you hazard free. So you add this group here. So now when you get to the expression, what you're going to get instead is f of P, Q, and R, which is also going to be 2 equal to, well, first this group here, so 1 and 1, is covered by Q, so it's Q, times is covered by R, so times R, and it's half inside and half outside P, so I'm gonna leave P alone, plus let's see, this group of 2 here, so those two, Q is covered entirely, so Q times is half inside and half outside R, so I'm gonna leave R alone, and it's entirely covered by P, so times P. And then I'm gonna have this final group here, which is 1, 1, those two. It's half inside, half outside of Q, so I'm gonna leave Q alone. It's completely outside of R, so I'm gonna put R naught, times, and it's completely inside P, so I'm gonna put times P. So this one is gonna be our final expression, which is actually different from the one we started with, which was QR plus PR naught. This circuit here does the exact same thing. However, it has not only QR, but it has Q times P. So basically it has an additional AND gate which takes Q ANDed with P. And it solves this problem here caused by the delay that this NOT gate is actually introducing. The circuit in this case will be like this. We will still have P, we will still have R going with a NOT into this, and we will still have you know, the QR with the R fitting into this gate and a Q fitting into this gate. But now we're also going to have an additional AND gate which takes the input from P Let me draw it properly. Okay, like this. It takes the input from P because it's QP, and also the other input from Q. So from Q as well. So now we have this additional AND gate, which gives us P times Q, which is this term here, and goes straight to, oops, you're not gonna have this was an example, okay, to our OR gate here, okay, to our OR gate here. Now with this, we're not gonna have the static hazard. Because, you know, in this case where we have added an additional logic gate, so an AND gate, which is going to take care of our hazard. So you can basically see that the static one hazard that we had here can be easily removed by introducing some more terms, so logic gates, to the function, so to our circuit. Basically, you know, you generally want to do this and check with the Carnot map if there are, you know, two ones, one close to the other, from two different group of minter of prime implicants. So in this case, I was looking at min terms, so the one is going to be the same for zeros. And you really want to do that. So, you know, when you're gonna make Carnot map and perhaps a truth table out of a function or stuff like that, just please think about hazards. Hazards can be of well, basically two types, well, more than two types, but anyway. The most common one are static one hazard and static zero hazard. Then there are other types of hazards which are called dynamic hazards, but those are more complicated, and I'm not going to talk about them right now. But, you know, you get the idea, you get the whole point here, that because of the delay, there can be unexpected moments in which the circuit is going to do something unexpected. So you may want to add more circuitry, so more logic gates, and check for them using the Carnot maps. So yeah, this is pretty much it for this episode.